I'm very happy to be here, largely for selfish reasons, because here are all the questions that you already know exist in open source. So I don't need, there's zero context setting. I can just jump into the fun stuff. Uh, so I'm just going to share screen here and show you Moss, and then hopefully uh, have a little bit of a discussion and go from there. Everything that I'll be showing you as I try and find the right screen to share I hope to have in a format that we can actually play with down in New York for the UN event in the middle of June. That said, I just made some changes this past week, and they broke some stuff that I didn't know they broke. And so maybe we'll stick that with a maybe. It'll be good to go like that. But I do have a version that's operating that we can have some fun with. So I spend a lot of time talking to people who develop technology, and a lot of these people want to build technology that advances open science and open source software. One of the issues they have is they don't live in either of those worlds. They live in product development world. That said, they have some pretty interesting practices in product development world, which I know some of you are very familiar with, where they just build stuff. They do not think about it, which can be beneficial or detrimental. Uh, I think there are many more benefits to it than drawbacks, and particularly if you balance it with the more typical or traditional research, open source, open science world, which is much more cautious, much more conservative, much slower to move. So the thinking behind Moss and the thinking behind some of the other things I'll show you that are informing Moss is that let's just build a thing. Let's just keep building the thing and uh, break, let it break. You know, make a change. The change was to be able to ingest 8,500 papers, and we can now ingest 8,500 papers, but I can no longer run some of the queries that I ran before. So something broke. We can go back and fix that thing, but then we can ingest 8,500 papers and run the queries. Uh, so keep that in the back of our heads as we're going through this. All of this is very early, just hacking something together to make it work, to get some really cool results and prove what's possible. So with that said, this is the repo, NumFOCUS/Moss. I'm the program manager of the Open Source Science Initiative, which is the sort of lead program developing this project. But this project will eventually spin off into its own project. Our contributors are, I would say, many at this point. We've got 8 or 9 folks. Some good first issues if you want to come in and contribute. Some of them are more scrappy than others. We're just getting our governance set up, our code of conducts, our community. It's really turning into an open source project, which is absolutely lovely. And the goal of Moss, and this is what it looks like, is to navigate the open source science world. So before I actually dive into what this version of Moss is, there's 2 versions. There's this one that I'm showing you right now, which is the sort of robust version. It's got a very nice backend. It's got a database. It runs on Postgres. It's fairly complex, but it doesn't really have a pretty front end because we're developing that back end. The second version is called Baby Moss, and this is what I use to showcase the potential of what we're building at events. I was just at PyCon showing this off. And this has a very, very good front end. It has a very good visual and UI. You can see the nodes. You can see the different element types, the different connection types between all these nodes. Its back end is a Google Sheet. So not much you can do with a Google Sheet once you get to the complexity that we're getting at. So you can already see this scale, which is a couple thousand nodes and a couple thousand connections, is breaking this visualizer, which I'm using. It's called Kumu, by the way. It's kumu.io. It's a fantastic free tool for visualizing graphs and systems. If you ever need to showcase your department or show the interactions within the university to anyone in administration, I would highly recommend you use this tool. Again, it's free and it's just so easy to use. There's just like a couple settings. Reach out to me. I'm happy to walk you through some of the stuff you'd need to use. But I'll start here with Baby Moss because the end result makes it much easier to describe what it is we're trying to do. So you're looking at this fairly complex hairball, this complex web of connections. And as I already alluded to, we've got the nodes over here. So we've got people, projects, institutions, papers, domain fields, subfields, and topics. Those are all grouped together. That's coming from OpenAlex. The way that they categorize research, or what they call works, so I'm going to say works moving forward, is you have a topic that is associated with a work, and there's generally only one, maybe two works per topic. They're very, very granular. Then you have a subfield, a little less granular. Then you have a field. I think data science would be a field. And then you have a domain, and there's only like 5 domains. So data science is a field, and I think the physical science domain. And it's a hierarchical sort of mapping. So if you say that a work is connected to a topic, you can immediately determine what subfield, field, and domain that work is part. So that's what all of these are. Then we have outcomes. This was a special thing for PyCon, so I probably won't include that, but it's still very interesting. There's a story to it I'll share with you. And then you have all the connections down here. So we've got all these nodes, these elements, and then we're connecting them to one another. So is a project or a repo, open source project connected to a paper? Is a person connected to a repo or a project? Is a project connected to an institution? Is a paper connected to a domain, field, subfield, topic? Is a person connected to a paper? What papers do papers cite? All the citation graph related to works, and funding data, who usage data, things like that. We have dependency data as well, though that's not on this map. So MOSS, the map of open source science, is taking in all these elements, all these connections, and mashing them together to build a giant knowledge graph of everything that exists. Because the reality of our world right now, where we all work, is that we've got GitHub. That is an API input. That is a repository for repositories. Other repositories for repositories are GitLabs, also things like that. So you have the repositories of repositories, then you have the repositories of works, where you have maybe Crossref, you have OpenAlex, you have a bunch of others. Then you have citation, like DOI assigners, you have DataCite and Zenodo and all these other entities that help give PIDs to all this stuff. And then eventually we want to get patents up here as a node. So we're going to have other endpoints, other repositories for patent data. And we're going to want to get economic data up on there. What patents produce what economic output? And that's going to be a separate repository. So we've got all these different places where we want to gather data, and no singular place where we can combine all that data to get interesting insights through that combination. So what MOSS is combining all those endpoints into one single place that we can query and ask questions to and learn from through those questions. One of my favorite sort of goals for this project is to be able to show the economic output of toothpaste, and then be able to show what patents are behind toothpaste. So at the university setting, we can already see tech transfer offices getting involved there. Then what translational research was involved in getting those patents, what foundational research was used for that translation, and what open source software was used for that foundational research. And then we can even go further, what mathematics, like theory, was used to create that software. And if we can show that whole provenance chain, we can go to a politician or a decision maker, a funder, and say, if you like the economic output of toothpaste, or frankly, if you just like brushing your teeth and having clean teeth, well, then you need open source software. Because if we take NumPy out of this provenance tree, we have no research that led to toothpaste. And then ultimately we can fund math theory, which would be fun as well. So that's what we're looking at right here. So this is the NumFOCUS ecosystem. We've got all these orange nodes. And in fact, I'm going to go to the babier MOSS because I'm already seeing it start to lag. So this is a much smaller graph. Same nodes, same connections, just much less data. So we've got these orange nodes over here. These are all the NumFOCUS projects. Trying to zoom in far enough for their names to appear, but that might not happen today. So make them stop dancing. You've got OpenFHE, BLOSK, etc. These are NumFOCUS projects, for anyone who doesn't know, are largely data science research projects, or data science research software. NumFOCUS is a fiscal sponsor for them. You've got NumFOCUS here, indicating that they fiscally sponsor It's this dashed green line. I'm pointing at my screen as you can see, but the dashed green line down in the key indicates fiscally sponsored. So all these projects are fiscally sponsored from NumFOCUS. Now we've got a project over here as well, CPython, not fiscally sponsored by NumFOCUS, but I've run an enrichment script which is relevant, very relevant to MOS, ingests a lot of the similar data, just not nearly as much. But we can see the people, the contributors to this project. Now, if we zoom out a little bit, we can see more of these projects, and we can see that some open source contributors contributed to multiple projects. And in fact, in here, we can see some people seem to be nexus points for entire subsystems within open source. This is a bot, so that's a bad example. I know Zach is in here, so let me find Zach. There we go. Let me get the Zoom thing out of the way. And it's not listening. There we go. All right, so we've got Zach is one of those 4 dots. There he is. That contributes to these 3 projects. Great person to reach out to if you want to learn anything about those 3 projects. And when you see this in the NumFOCUS ecosystem, you can look at maybe these nodes over here. These seem to be experts in data science software in some way or another. Like you can really dive into this connection data, this relationship data among different projects, and very quickly at a glance, figure out who you want to talk to learn about a specific visualization software or something. Fantastic. So we've got people connected to projects. I don't have any papers in this submap, so I'll go back over to the big map in just a second. But what we can see over here, all of these are things that people input while at PyCon. And I think if I click that off, we'll see names. Hey, look at that. Okay. So you can see an institution here. This person came over. They're affiliated with the University of Pittsburgh. They contribute to SciPy. SciPy is used to determine how people communicate while gaming, along with NumPy and it looks like pandas. So someone used these projects to do this thing. And University of Pittsburgh was involved. A lot of fun. As we get more of the data, these types of what seem like very simple connections at this point become very informative because you can see what type of relationship was University of Pittsburgh in this outcome. Does this person work here? Are they faculty here? Are they a student here? Or does the University of Pittsburgh directly fund this? It doesn't look like it because there's not a direct connection there. But we can do bridge relationships and see maybe if there is. So just to humanize this a little bit, because we're about to get even further into the data, here's a node. Yeah, it's this one. Determines the community desires for the future of the community. There's a couple other community-based ones. Determined different perspectives of community development related to geographic location and various indicators / segmenters. These 2 projects used this open source software to do really cool stuff related to getting solving very local problems in communities. They were done by a high school student who was at PyCon, whose name is Blue, who is affiliated with Arlington Tech. And the connections, unfortunately, this is a small map, so I wasn't worried about troubleshooting the connections to Blue, and those didn't show up. But it's really cool. When Blue was telling me all the stuff that she did with this software, so I was inputting it on this Google sheet, just like typing away, which she found fun because she just learned about Excel anyway. But once it popped up on the map, just like the excitement lit up in her face. It's very impactful to see your impact outside of a spreadsheet. So it just meant a lot. I don't know. That was my favorite part of PyCon. So this is, again, just to show what the potential is once we get all this data in a nice visual with nodes and relationships. So we're going to leave pretty visual land. No, we're not. Sorry. I promise to show you papers. So these are all the NumFOCUS projects. We come down here to this little blob. You notice there are a bunch more nodes, and they're all topics, subfields, fields, and domains. Not every piece of software has a DOI in the repository. It's shocking. I know. There's poor practices in registering and citing software. So any of these that are outside of this big pink blob don't have DOIs in them. Or rather, it's more complex and nuanced than that. Because if it has a Zenodo DOI, it technically has a DOI, but I can't pull that DOI directly from OpenAlex. I have to use a really complex script to just get the papers that cite that DOI because it's very annoying. Our infrastructure needs some improvement. But these projects down here, let's assume all these projects don't have DOIs in them. These projects in here have easily parsable and scriptable, scrapable DOI formats in the repository. So we're able to pull all their information related to the papers that cite that repository, related to the papers that cite the papers that cite the repository, related to the authors that wrote that original paper, related to the authors that wrote the citing paper, where they work, what the relationship is with that institution, the other papers they've written, where they were when they wrote those papers. All of a sudden you enter the academia world where there is vast amounts of data. And we can use that data to infer stuff about open source software that could be right or could be wrong. The point of MOSS is to give access to that data to everyone in this call in a user-friendly way so you can make that decision. You can write that algorithm, that script, that query that says, look at all the papers that cite the paper that cite this repository DOI, look at their fields, count the number of fields that those papers are associated with, and add them up. And whichever field is the highest, assign that field to the repository. That's a script that currently works with MOSS. We can do it. Well, I might not be able to do it in this demo because that's one of the things that just broke, but it can be done, I promise. It's not accurate. Like, it's not the truth. It is a perspective on this data. And what MOSS is here to do is let all of the perspectives on the data exist side by side in a very accessible way. So you could write that query in just or sort of upload it to MOSS as because MOSS is a shared service, and someone else could then run that same query over a different repository, or you could run someone else's query over your repository. It's a lot of fun, and that's what we're going to look at now as we leave this pretty mess. Let's look at all the nice colors and connections, and we go into data land, where we have, again, a robust backend, almost zero effort put into the front end. The goal here was just to give a relatively straightforward way to interact with some of the APIs involved with MOSS. So what can you do with MOSS? You can ingest stuff. I don't have the workers running in the background, so I won't run an ingestion right now. But you put in the GitHub repository URL, you click ingest, and it sends it off to a bunch of Celery workers, just a bunch of bots that go and pull the data over a course of time. You come back in 5-10 minutes, and all the data on that repository has been ingested. I mean all the data, everything but the actual code. We're ingesting all the comments, all the issues, all the text related to those, and literally everything but the code that we can pull from GitHub, because the queries we can run over that data is fantastic. And one day we do want to ingest the code as well. That's a lot, so let's just keep that to one day. It currently ingests directly from GitHub, but we are working to make it so it's ingesting from ecosystems, which if anyone knows what that URL is, if you could throw it in the chat, be fantastic, because ecosystems is an amazing tool for getting data about GitHub repositories, or not just GitHub, software repositories, and so much more. And so when we switch to ecosystems, which is my task for this week, we can ingest much more data much more quickly, because GitHub has rate limits. You can only ingest so much data from GitHub before you're basically banned from ingesting data for a little bit, which means I can go one NumFOCUS project every hour. And there's 60 sponsored NumFOCUS projects and 100 and some odd affiliated projects. It will take me too long to do that, so we're switching. Another way you can ingest by keywords. So this relates to trying to find open source software in this context related to your institution. So when people create software on GitHub, as we all know, they don't give it metadata, they don't give it DOIs, as we just saw. They definitely don't give it a ROR, an identifier for your institution. Sometimes, more often than not, actually, they'll put the words of the university in some form either it's the acronym or it's the full like name of the university or institution in the repo README somewhere, or in their username, like description. Sometimes, almost never, they will create the repository under an organization that's owned by a university. If that's the case, fantastic. We can figure out what what repositories are produced out of that institution just by looking for owners or repositories made with the owners that's affiliated with the institution. For every other case, we have to run algorithms to infer with a degree of confidence what software is affiliated with what institution. So one of the most simple ways to make this inference is through keyword analysis. So you search for University of Vermont, and the script, so you put that in right here. The script will search GitHub and ingest every repo and all the data related to the repos and all DOI data found. So all the works and the citing works and the authors related to any DOI found in a repository that has University of Vermont somewhere in it. You can also ask it, you can't do this in the UI, but you can ask it to look for repositories that have people that are like have core contributors who have put a university in their keyword in their description. So that's another way to assume an affiliation. So that's it. Let's just stop there. I could keep going on any of these points forever. So please keep questions in the back of your head. I'm happy to dive deep on anything. So you can ingest by a repository URL. You can ingest by a keyword. Once you run the ingestion, I'm going to try and switch sharing screens here really quick. You end up with a bunch of data. Don't worry too much about this. I'll be out of here in just a second. But for anyone who is interested in formats of the database, the data comes into a Postgres database. We have no marriage to Postgres. Postgres is just the easiest thing to stand up, which is weird to say. And we're looking at whether or not we want to do something like Kuzu, not Kumu, Kuzu. SurrealDB is another option. Neo4j is another option. The stage we're at with Moss right now is just get a bunch of data, play with it, fix the models, fix the schemas, right? Iterate rapidly until we figure out exactly what we need and then find the database that matches that. It's a little different than the really architect and plan from the beginning. There was a lot of architecture that went into Moss, but the specific database we're going to use, not really important for now. So the switching back screen share, so just a second. The data comes in to that database. And now that the data is in that database, which currently is 16 gigabytes large, and I erase it almost every day as I play with this, you can search it. So my favorite repository to search is OpenFold. You can see there's a paper related to OpenFold. There is a repository related to OpenFold. If I click it, I get a bunch of the data. This is not all the data related to this repository in the database, but is just proof that we can surface stuff. Because again, to iterate means just show that something works and move on. We can come back and make it really good later. So it's got an ID in our database. We've got the GitHub ID of the project. We've got the description, all the stuff. It's cited by 125 citations. It got a new citation. Congratulations, OpenFold. It's usually 124. Here's the linked scholarly works. That means this DOI was found, there it is. This DOI was found in the repository metadata. So I think this one's in the README file. It might have a citation CFF file. Repository sharing contributors. I'm not sure this is accurate, but it works in concept. It probably just needs some refinement. But again, iterate, show it works in concept, move on. Let's get this thing built and then go back and fix all the things that need fixing. Repository share link worked, etc. And here's, it's not even going to show up. The cute little visual that we have in here is very funny when it renders. But the idea is eventually there will be a good visual here, similar to what you saw with Kumu. Okay, so we've got repository. Let's go back. I am admittedly afraid to hit the back button because I'm not sure what's going to break when I do. Here's the work data. So we've got the ID, the OpenAlex ID. OpenAlex is the primary source we're using for data, metadata related to works. cited by count, etc. Work cited by this work. So the DOI found in the OpenFold repository cites 63 other DOIs. People citing this work, so this definitely isn't accurate, but I've gotten it to work before. I just keep breaking it. The idea here is the authors of the papers that cite this DOI is a relevant data point because you can then see where that person goes in their career. You can see the institutions that they work at, and you can infer that an institution is, if there are researchers who themselves publish research, you can then infer that an institution outside of your own is using the repository that was created from within your institution, which I think is something that people would like to show to decision makers in institutions. And that's what this is right here. Oh, yes, it rendered. It's a small graph, so it kind of makes sense. If there's a lot of stuff here, it like goes way off the screen horizontally and vertically. There's colors everywhere. It's really weird. But relationship graph. All right, so we've looked at a repository. We've looked at a paper. We've searched the database. This is where it gets really interesting in my mind. Where do we want to start here? Let's start with just typical recipes or analysis algorithms. These are things, these are the algorithms I was talking about before. An easy one, two easy examples are impact and health. How do you determine the impact of anything? How do you determine the health of anything? Right? This is why we get second opinions at doctors. One doctor says you're healthy. You're like, I want a second opinion. You go to another one. They use a completely different algorithm to assess you and say, hopefully you're healthy as well. But then with the two combined, you're confident that you're healthy. Same with the impact. With research, we have impact factor, H index. We have all these weird things that are just kind of imposed upon us as impact algorithms that have been really monolithic. But we have other stuff coming up from the bottom, from the grassroots, which is things like altmetrics and a bunch of really good work going into how to measure the impact of research and software. We want to help that work elevate to the level of those monolithic algorithms. So create your own. Use the data that we're sharing and create your own. We're going to make a very simple way to create an algorithm, like just typing in natural language or filling out a form. We're not nearly to that stage of development yet. But here are some examples that we've put together just ourselves. Just take a second. So we can run these on any repository in the database and get answers. So let's do engage non-PR contributors. And I'm going to stretch my memory. I think OpenFold is 1075. It is. It doesn't say it's OpenFold, but I know these contributors. These are the people that have contributed to that project. No. They haven't contributed. They've created an issue, but have not contributed to the project. So they're users. They use this software enough to say, hey, could you add this feature or could you fix this bug? And then they consume that work from the maintainers and developers, and they use the software. That's amazing. This is a really good metric to use to indicate the importance of a piece of software. And you can do this in any random repository. Just do number 3. So this one, many fewer issues. OpenFold is a very popular project. This one less so. Let's look at repo health. Let's do that same repository. And this wasn't working earlier. I think yes, I got it work. Okay. So that less popular project scored a, let's say 2.5 or a 25. Let's call this just 25 based on these metrics weighted this way. So these, I'm pointing at my screen again so you can see, these are the things that were put in that algorithm. You could create your own algorithm with these exact same things weighted differently. You could use different things and completely change the weighting because you have different things in there. And then very quickly just switch algorithms and run it over the same repository and get second opinions, third opinions, fourth opinions rapidly, and then make an aggregate of all those recipes. In fact, you could make a recipe of recipes which weights other sub-recipes. Like you could get really complex with this. And the key here is you're just selecting one and running it. once you get going. And then if someone at your institution or, my neighbor who's really good at this sort of thinking just builds one and uploads it, it can get really, really popular and it can replace impact factor. It could be like the lead measurement for impact of research software until 15 years from now, people learn how to game it. And then another one gets made and rises to the top. It creates a marketplace, so to speak, of algorithms. So now let's look at the health of OpenFold. I hope it's OpenFold because it's about to show the name. Yeah, all right. So OpenFold, as opposed to, and this is what we should expect, a much more popular project, almost has a 100 score. Say it's using the same recipe, so it's the same sort of indicators with the same weightings. That's a lot of fun. You can run any of these. Some of them, I should say that with a caveat, some of them definitely don't work right now. But a lot of these can be run. And it's a lot of fun. Let's just try one randomly, and this is where things will go horribly wrong. Let's do OpenFold. See, there should be an all option here, but let's say field. Let's say 10. Yeah, all right, it happens. So this one would return the you'd start with the DOI of OpenFold, you'd go to OpenAlex, you'd get all those papers, and then you'd get the topics and fields and domains of those papers, and then this would return that result. So what fields is OpenFold used in? What fields of research? A lot of fun. Last thing, before I do a quick wrap up, is the institution-centric workflow. This is where we start talking about affiliating a repository with an institution. And I haven't tested this in many weeks, and I've done a lot of work on that on this in the meanwhile, so this will break. So we're an institution. Let's do University of Vermont, because I know I ingested that one in this version. University of Vermont. Review and calculate affiliations for the University of Vermont. Here we have some little context that says, hey, no one's ever run an affiliation algorithm across the MOSS database connecting repositories with the University of Vermont. You're going to be the first one to do that. Fantastic. So let's run one. Let's run a keyword match. That's the algorithm I described earlier. Again, MOSS is providing the tools. We're not the experts in this. We're not going to be able to create the algorithms that truly affiliate a repository with an institution. That's up for y'all to figure out, and then upload those affiliation algorithms to MOSS and then use MOSS's database to run them. So here's a simple keyword match. Search for essentially repositories with University of Vermont in it. Let's run the keyword match. Yeah, doesn't work. It would return a list of repositories in the MOSS database with this keyword. And then if it returns like 2 or 3 repositories and you're like, no, there's definitely more repositories out there with these keywords, you can transition your affiliation algorithm into a discovery algorithm keyword search. So now once you run an ingestion, let's see if it does it. No, it will go off into GitHub land or repo land, find all the repositories with these keywords and say, do you want to ingest all of these into MOSS? Because they're clearly not currently in MOSS, at which point you would say yes. And it then ingest them into MOSS. MOSS is now richer thanks to you, and you can now run some analysis on repositories that might be affiliated with your institution. Then you click proceed to analysis, and it essentially brings you back to this screen where you get to choose recipes to run over it. You can filter, when you're doing this affiliation stuff, you can filter confidence thresholds of your affiliation algorithm, because nothing, unless it's a repo created under an institutionally owned organization on like GitHub, you're never going to have a 1 confidence. So this keyword algorithm counts the number of mentions of a keyword in a repository, and the more mentions there are, the more confident it is that it's affiliated. Obviously not like good, but something. So some will have like a 0.1 affiliation, others confidence affiliation, others will have a 0.9. So that's like 1 mention versus 9 mentions. You can change the threshold, and then you can run analysis only on all the repositories that come back above a certain threshold. So you're not analyzing a bunch of student projects or a bunch of whatever, because a lot of these affiliation algorithms can include sorting from student projects, syllabuses. There's so many syllabi in GitHub, and actual projects that are used. When I run the search with University of Vermont, it returns all syllabi and like student projects except for one project, which is used to model floodplains, which is relevant here in Vermont. We're starting to flood every year. It's really sad, but it works in that research, that actual research software is at the top of the confidence threshold. It's like you want to analyze this one. These other ones, think about, go look at a little further, but you definitely want to analyze this one. This is great research. This is great software likely affiliated with your research. So that is a lot. That is too much to share all at once. So I apologize right off the bat. But to wrap this all up, we have this back end. This is Moss. We have this baby front end, which I am happy to work with anyone if you need to do like a presentation on some data related to your university or your institution. I'm happy to work with anyone to put together a very simple visual for this, because truly it's just a spreadsheet. And at this point, I've gotten very good at spreadsheets, and there's a little CSS code and some like point and click stuff to make these visuals. Then we have the work behind Moss. So we have the Moss repo itself. It's a lot of fun. We meet on Wednesdays. Every Wednesday is a dev call. We meet once monthly on Monday. That's like overview call for people who are just interested in the project and want to get updates. The dev call is a lot of fun. We get together and just kind of talk about databases. Maybe that's not fun for everyone. Then there is the realization that Moss is one element in a much more complex solution that's needed to the problems we're facing. To answer the questions that I put in chat that I usually start with for context setting, we need, frankly, brand new infrastructure for software, for data storage, for accreditation, for credit, for PIDs. We need a lot of new different types of infrastructure, and we need the people who currently use the current infrastructure to just frickin' put DOIs in your repo, use best practices. But we can't blame them, because the best practices are not easy to do. It's not easy to create software metadata. It's like, I manage this repository. I haven't done it yet. It's a task. I'm not going to do it, frankly, until it's easy to do. So the other work that I do, some with NumFOCUS, some with some other orgs, most of it, like orgs are just a background. Most of it is just as an individual that really wants to see science be more accessible and impactful and relevant to the communities that it's supposed to impact and influence, involves figuring out how to do the rest of this stuff. So this impact of research software innovation sprint, 6 to 9 months, we're working to figure out how to, we being these people as the track leads, we're working to try and figure out what software is used in research through software mentions. So not just DOIs, but software mentions. That's track 1. Track 2, we're trying to figure out how can we make it incredibly simple, if not invisible, when it comes to creating metadata for research software, so that John doesn't need to create a script to go off to 3 different DOI assigners and aggregators to figure out what papers cited this repository that already has a DOI. It should be simple. How do we do that? How do we make simple metadata in software repositories? This other innovation sprint, which hasn't started yet, is looking for track leads. The one I just showed you has been running for a couple months at this point. It's doing great work. This other one is related to resiliency of software and data infrastructure. Like, we're experiencing what happens when the infrastructure we depend on goes away for one reason or another. And political climates are just one thing that can happen to infrastructure. There's a lot of other things that can cause a rug to come out from everyone when it comes to infrastructure. So how can we make it so this situation never happens again, regardless of the circumstances? That's what this sprint's about, working with some folks who are running triage on current things that are losing funding and storage and all that stuff. So hats off to them, and we want to help them in any way we can. And these sprints follow the same sort of philosophy. Let's just build something. We don't need a theory. Let's just build something, break something else, and then fix it. And we've ended up with some software. So we've got research software metadata analysis. This is used Andrew's ecosystems to figure out that we've got 40,000 citation CFF repositories. We've got 3,000, I think it's 3,000, it's either 3,000 or 1,300 code meta.json repositories, and we've got a couple other Zenodo.json repositories. And we now know which repositories fill out which fields. And with that data, we can now go on. First of all, we can write a paper, which is going to make a lot of people happy. But we can also go on and build a tool for fixing the gaps in the metadata. And we can figure out, are LLMs actually good at auto-populating metadata? And to that end, I invite you all to an event, which I don't have up here, but I'll type in really quick. Happening in Chicago. If you're in the neighborhood, I wouldn't go out of your way too much. It's a half-day event. It's a workshop we're doing at IEEE's eScience 2025 on automated metadata generation, data discovery. Should be a lot of fun. Okay, I'm sorry. I talked for 40 minutes there. Happy to answer any question.